Hi class, this is Dr. O'Connor. This video is going to substitute for Friday's lecture on October 14th. So I expect everyone to watch it. I'm going to go through sections 5.1 to section 5.5, so 5.6 will not be included here. Well, we need to understand how electrons are distributed in an atom in order to explain the formation of ions and molecules. To understand the formation of chemical bonds, we need to know about the electronic structure of atoms. Our present theory of electronic structure started with explanations of colored light that was produced in hot gases and flames. Here, we're going to first describe the wave nature of light, and then we'll talk about the different phenomena of light being emitted from solid objects, for example, at certain temperatures. So we all know that when we drop a stone into a quiet body of water like a lake or a pond, the result is an up and down motion of the surface of the water. That up and down motion will travel outward from where the stone hit the water. Go ahead and try this. This is an example of a wave. So a wave is a continuously repeating change or oscillation in matter or in a physical field. Light is considered a wave. Light consists of oscillations in electric and magnetic fields that travel through space. The electromagnetic spectrum consists of visible light, X-rays, radio waves, microwaves, and so on. We'll talk about that in a second. A wave is characterized by its wavelength and its frequency, and we represent the frequency with the letter mu and the wavelength with lambda. So the wavelength is the distance between two adjacent peaks or troughs of a wave. So for example, this would be considered a wavelength, or from here to here would be the length of the wave. The frequency of the wave is the number of wavelengths that wave will pass a fixed point in 1 unit of time, usually in a second. And we know that frequency has the unit hertz or reciprocal seconds. As far as the amplitude, that is the height of a wave. And when we're talking about light waves, you can think of amplitude as being the intensity, the brightness, or the dimness of that light wave. Now, we can relate the frequency and the wavelength to its speed, to the speed. So frequency and wavelength are inversely related. The longer the wavelength, the lower the frequency, and vice versa. The product of the frequency and the wavelength is the total length of the wave that is past a given point in 1 second. This is the speed of the wave. Now, the speed of light is constant in a vacuum, and it is given this value right here. And we usually round that to 3.00 times 10 to the 8th meters per second. So the speed of a light wave is dependent on the medium through which it passes. And again, it just so happens in a vacuum, the speed is 3.00 times 10 to the 8th meters per second. Actually, the speed in air is slightly less, so for our purposes, we will use this value here when we do our calculations. Let's take a look here at the electromagnetic spectrum. And here we go. The range of frequencies or wavelengths of electromagnetic radiation is called the electromagnetic spectrum. We can see from here that visible light, which is just a small portion of the spectrum, extends from the violet end of the spectrum, about 400 nanometers, 380, to the red end of the spectrum, about 780 nanometers. Outside of this range, electromagnetic radiation is not going to be visible to the human eye. Infrared radiation has wavelengths greater than the wavelength of red light, and ultraviolet radiation has wavelengths less than the wavelength of ultraviolet light. So I would expect you to know these regions. And so we know that starting from left to right, we have gamma rays, X-rays, ultraviolet, the visible region, infrared, microwave, and radio waves. And we see that the wavelengths from left to right. So for example, radio waves have much longer wavelengths than do X-rays. Also note that from left to right, the frequencies decrease. So we see that X-rays have higher frequency than do microwaves. So I would expect you to be able to tell me which has a higher frequency or a longer wavelength when you compare these gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. White light, it includes all of the wavelengths of light in the visible spectrum. One example is sunlight. So let's just go ahead and sum this up for a minute. Longer wavelengths, lower frequencies. Shorter wavelengths, higher frequencies. And we can relate frequency to energy, which we will do in a few minutes. High frequency corresponds to high energy. Lower frequencies correspond to lower energy. So going back to our electromagnetic spectrum here, we can see that X-rays have higher energy or more energy than do microwaves. Ultraviolet is higher in energy than infrared. Let's go ahead and do a problem using this relationship here. Here we're told that most of the light from a sodium vapor lamp has a wavelength of 589 nanometers. What is the frequency of this radiation? So the first thing we need to do is, because C is in meters per second, the wavelength must be converted to meters. Then we have C, and then the frequency, we solve for frequency, and that's equal to C divided by the wavelength. And we go ahead and perform that calculation. We end up with 5.09 times 10 to the 14th reciprocal seconds, which is the same as 5.9 times 10 to the 14th hertz. Here's another problem. We're told that an FM radio station broadcasts at a frequency of 91.5 megahertz. What is the wavelength of these radio waves in meters? So in this case here, we're just going to solve for wavelength, and that's going to be C over the frequency. And notice the frequency here is in megahertz, and we need to get that into hertz or reciprocal seconds. So this is the same as 91.5 times 10 to the 6 hertz or reciprocal seconds. So we're all set to go. So we have 3.00 times 10 to the 8th meters per second divided by that frequency, 91.5 times 10 to the 6th reciprocal seconds, and our wavelength is 3.28 meters. So now you know how you can use this. You can determine, if you know the wavelengths, you can determine the frequency and vice versa. Let's go ahead and talk about the classical distinction between energy and matter. Basically, matter, we know it comes in chunks. We can hold it, we can weigh it, we can change the quantity piece by piece. And we know that matter moves in specific paths. Energy, on the other hand, according to classical theory, was massless. Quantity can change continuously, and also light would travel in diffuse waves. We need to talk about a little terminology here and about the different behaviors of waves and particles. And you know, Isaac Newton studied the properties of light back in the 17th century, and he thought that light consisted of a beam of particles. Before we talk about that, let's talk about refraction and diffraction. So as far as refraction goes, we already know that light of a given wavelength will travel at different speeds through a medium, depending on what that medium is. So it's going to travel at a different speed in a vacuum than it would in air or water or glass or so on. So here we show a light wave going from one medium, air, to another, which is water. So when a light wave passes from one medium to another, the speed of the wave changes. And this causes a change in the direction of travel. And this is what we call refraction. So here we can measure the angle of refraction, and this angle is going to depend on the two media and of course the wavelength of the light. Now, on the other hand, if we throw a stone into a pond, it does not undergo refraction. It's going to continue to gradually slow down along the same curved path once it enters the water. So we don't observe refraction when it comes to matter. Another phenomena is dispersion, and dispersion is when white light separates into its component wavelengths or its colors when it's passed through a prism. And this is because each wavelength or each wave is refracted at a slightly different angle. So if we notice here that red is going to be bent least while violet bends a little bit more. So a rainbow would be an example of this. Then we talk about diffraction. And diffraction is a property of waves in which the waves will spread out when they enter an obstruction or small hole about the size of the wavelength. We observe diffraction when we look through a mesh curtain, like a sheer curtain or lace curtain, and we look through that curtain at a street light. We notice that the image of the street light is blurred, and this is due to what we call diffraction. As far as diffraction goes, if we have two slits, let's say, so we have these two slits, and again, they're about the size of the wavelength, and so the light passes through these slits, and what we can have is something called constructive or destructive interference. As the waves spread out when they encounter these small slits, then if the waves, the light waves, are in phase, okay, like up here, all right, what they do is add up. They add to one another, and they cause a bright spot here on this film. And if the waves are out of phase, like they are right here, then what'll happen is they cancel one another out, and you end up with these dark spots on the film. So this results in what we call a diffraction pattern. So this is constructive interference, constructive, the waves add, and this is destructive, the waves cancel one another out. So basically here the amplitudes will add to form the bright region. Here they will add to form the darker region. So again, the result is what we call a diffraction pattern. Now, in the early part of the 20th century, the wave theory of light was the model used. But in 1905, Albert Einstein was able to explain what we call the photoelectric effect by postulating that light had both wave and particle properties. He based his work on that of Max Planck, who derived a theoretical formula that described the intensity of light of various frequencies that were emitted by a hot solid at different temperatures. So in earlier times, other scientists had shown that the light of maximum intensity from a hot solid is going to vary in a definite way with temperature. So here, let's take a look at this. Here we see hot coals. They tend to glow red, and the temperature is about 1,000 Kelvin. If we increase the temperature by about 500 Kelvin, here we see the element from an electric stove, and we see that the light emitted is more orange. And then finally, if we increase the temperature even more, what we observe is whiter light, and an example would be a light bulb. So at lower temperatures, we have mostly red light emitted. At higher temperatures, we get more yellow and blue light that becomes mixed with the red, which provides white light. Planck theorized that the atoms of a crystalline solid actually vibrate, or oscillate if you will, with a definite frequency, which is going to depend on the identity of the solid. He actually reproduced the experiment on glowing solids by postulating that a vibrating atom could only have certain energies allowed by this formula here. So we have the energy is equal to N times H times the frequency. So capital E is the energy, N is a positive integer. It can be 1, 2, 3, 4, and so on. And H is a proportionality constant called Planck's constant, and it is equal to 6.626 times 10 to the negative 34 joules times seconds. What this is saying is that the only energies an atom can have are H nu, 2H nu, 3H nu, 4H nu, and so on. Let me say something else about N. The numbers symbolized by N are called quantum numbers. And the vibrational energies of the atoms are what we call quantized. That means that the energy values are limited to certain values. You know, in everyday life, we're not used to quantization. And think about it. Think about a car. Let's say your car can only travel at 10 miles per hour, 20 miles per hour, 30 miles per hour, but nothing in between. It couldn't travel at 12 miles per hour, 23 miles per hour, or 35 miles per hour, or any other intermediate speed. As we know, that's not reasonable for car energies, but guess what? It is for atoms. So for atoms, the rule is quantization. So in other words, the energy of that atom, it could be 2H nu or 3H nu, but it couldn't be 2.5 or 2 1/4 or 2 3/4. It's either 2 or 3, 3 or 4, nothing in between. Like every day quantities, like for example speed, it's a ramp. As far as energies of atoms, you can think of them as stairs. Can have this energy, this energy, this energy, but nothing in between. As we stated before, the energy of an atom is quantized. The energy is not continuous. The change in an atom's energy occurs when the atom absorbs or emits one or more packets or definite amounts of energy. This here would be a packet of energy. And this energy packet is called a quantum. It's a fixed quantity. The plural is quanta. So I have several quanta, or I have a quantum. So again, the quantum of energy is equal to H nu, and an atom changes its energy state by absorbing or emitting one or more quanta. The energy of the absorbed or the emitted radiation is equal to the difference in the atom's energy states. It turns out that Planck was not convinced with the assumption of quantization, and he tried to actually eliminate it from his theory. Einstein extended Planck's work to include light structure. His reasoning was this: if a vibrating atom changed energy from, let's say, 3H nu to 4H nu, it would increase in energy, and the energy would be absorbed as a quantum of light energy. If the energy of the vibrating atom changed from, let's say, 4HV down to 3HV, there would be a decrease in energy, and the energy would be emitted as a quantum of light energy. These quanta are called photons, okay? Or we can think of them as particles of energy that are proportional to the observed frequency of light. And that is stated right here. This is a very important relationship, okay? And here, this is just the change in energy in relationship to the wavelength, right? We now know that light consists of quanta, which we call photons, and the energy is proportional to the frequency of the light. Remember, H is Planck's constant. That's our proportionality constant. In 1905, Einstein used the concept of photons to explain the photoelectric effect. The photoelectric effect is the ejection of electrons from the surface of a metal or some other material when light is shined on it. The electrons are ejected only if the frequency of the light exceeds a certain threshold value, which will be characteristic of the particular metal or substance. So one example is a photon of red light has insufficient energy to eject an electron from potassium metal. However, violet light, which we know is more energetic than red light, will cause the potassium metal to eject electrons. The amount of energy required to eject an electron is what we call the work function. Let me write that out here. So that energy required is called the work function, and it is, that's a terrible, represented with this symbol here. Let's see, let's redraw that. A little bit better. Okay, so it's represented with this symbol here, and it's called the work function of the metal, and usually it's in units of electron volts, or you can put it in units of kilojoules per mole. The work function, it's an energy, right? So it's the work function, again, this would be proportional to H times the frequency, and it's going to be lowest for metals of group 1A and 2A. Why is that? That's because the electrons are held less tightly. The ionization energy is lower for those metals than it is for other metals towards the right-hand side of the periodic table. Einstein explained this dependence. Let me move that over. Einstein explained this dependence of the photoelectric effect on frequency by assuming that an electron is ejected from a metal when it is struck by a single photon. And of course, that photon must have at least enough energy to remove the electron from the attractive forces of the metal. Remember, that electron is going to be attracted to that nucleus. It doesn't matter how many photons strike the metal if no one single photon has sufficient energy. If it doesn't, if not one of those photons has that threshold energy, the electron will not be ejected. So the energy of the photon is only dependent on the frequency and the wavelength of light and not on the intensity. Remember, the amplitude is the intensity of the light, the brightness or the dimness of the light. The intensity of the light beam will tell us how many photons are in the beam, but remember, it is the frequency that measures the energy of the photon. So back to our example of the potassium metal, a photon of red light has insufficient energy to remove an electron from the potassium metal. A photon of the corresponding threshold frequency will have just enough energy, and at higher frequencies, it has more than enough energy to eject the electron. So the photon hits the metal, and the energy of the photon is taken up by the electron. The photon then will cease to exist as a particle, and it is said to be absorbed by the electron. So the energy has been absorbed by the electron. So what we see is the electron is transitioned from a lower to a higher energy state. So this shows us that the wave and particle views of light are regarded as complementary views of the same physical entity. We call this the wave-particle duality of light. The equation, E is equal to h nu, displays the duality. The energy, or capital E, let me write this out. E is h nu. The energy, or E, is the energy of the light particle or the photon, and this is the frequency of the associated wave. A complete description of light cannot be explained by the wave or the particle view alone. We have to combine the two. In summary, an atom has only certain quantities of energy. Its energy can be changed only by absorbing or emitting a photon. The energy of the photon must equal the change in the energy of the atom. Here we're told that the red spectral line of lithium occurs at 671 nanometers. Calculate the energy of one photon of this light. Well, in order to do that, we need to determine the frequency of the light, or we can just go ahead and plug this in for the frequency, okay, which is fine, but I'm going to take this stepwise so you can see what I'm doing. So the frequency is 4.47 times 10 to the 14th hertz. And we know that the energy of one photon is equal to this. This is the energy for one photon. So we have h, Planck's constant, multiplied by the frequency, and we end up with 2.96 times 10 to the negative 19 joules. Okay, now we're being asked, what is the energy of 1 mole of these photons? Well, we know that 1 mole would contain 6.02 times 10 to the 23rd photons, right? So what we have is 6.02 times 10 to the 23rd photons. And we know that one photon of this particular light is 2.96 times 10 to the 19th joules, and this would be 178,192 joules, or better yet, 178 kilojoules for 1 mole of these photons. Oh yeah, there's another problem that I want to show you here. This has to do with the work function. So you can look this up. So the work function of copper metal is 437 kilojoules per mole. It is 279.7 kilojoules for lithium, which would require the higher frequency. So we need a, obviously one of these is going to need a higher frequency of radiation in order to eject an electron, okay? And which one would that be? Well, that would be for copper metal. It takes 437 kilojoules per mole of electrons. Lithium, 279. So it's going to take more energy to remove electrons from copper metal than it would from lithium metal, okay? So obviously the copper metal would require the higher frequency of light. Let's just go ahead and take a look at what that frequency of light would be. So for copper metal, we're given the energy here. So we can determine the frequency. The frequency would be the energy over Planck's constant, and that would be 437 kilojoules per mole. Now that's per mole, okay? And also we're in kilojoules. We need to get into joules here. So 1 kilojoule is 1,000 joules. And 1 mole is 6.02 times 10 to the 23rd photons. We would need to divide that then by Planck's constant, 6.626. See, the reason we had to convert from kilojoules to joules is because Planck's constant's in terms of joules. So we calculate this out. So we would need a frequency of 1.09 times 10 to the 15 hertz in order to eject an electron from the surface of copper metal. And what would that wavelength be? Well, the wavelength would be speed of light over the frequency. So 3 times 10 to the 8th meters per second over 1.09 times 10 to the 15 reciprocal seconds or hertz. And this would be 2.75 times 10 to the 7 meters. And this would be 275 nanometers. So this would be in what region? Would that be visible, infrared? No, it would be the ultraviolet region, okay? And I already did the calculation. So for lithium, we would need a wavelength of 428 nanometers, and then you could determine the frequency from that. So obviously we can eject an electron from lithium metal with a lower energy radiation or lower energy frequency. Okay, that would be in the visible region. So what are some applications of the photoelectric effect? Well, we have photocells. They turn lights on, like street lights, lights in your homes, exposure meters in cameras, and also solar cells. You know, remember, a solar cell converts radiant energy to electrical energy. So now what we're going to do is talk about atomic line spectra. And again, spectra is plural, where spectrum is singular. So if I'm talking about one particular spectrum, it would be a spectrum. But if I have several of these, it would be spectra. Anyway, the line spectrum of a hydrogen atom is relatively simple. It consists of only 4 lines in the visible region. And let's first define a continuous spectrum. This is a spectrum that contains light of all wavelengths. So a rainbow would be an example of that. A line spectrum, which is what we're talking about, shows only certain colors or specific wavelengths of light. Light emitted from a heated gas, let's say hydrogen gas, will result in a line spectrum. So here we have a line spectrum for hydrogen, and we see there are 4 lines in the visible region. One at 410, one at 434 nanometers, so we have one that corresponds to violet and blue light. One at 486 nanometers, that corresponds to green light, and one at 656 nanometers, which corresponds to red light. Before we talk about the Rydberg equation, let's go over here for a second. In the lab, you can do some simple flame tests. And for example, if I were to take an aqueous solution of strontium, let's say strontium chloride, we have strontium ions in that, and I'll dip a platinum wire into some of that, and then go ahead and put the wire into a flame of a Bunsen burner, what you'll notice is you'll notice a red flame color. So you'll see red in that flame. And the flame color, that red color, is due to the emission of light of a particular wavelength, in this case red light by strontium. In this case, this is green light by copper. And sodium, you would see an orange emission. Anybody who's ever cooked something on the stove that contains salt, and if that tends to boil over, you'll notice that your nice blue gas flame turns yellow. That's due to the emission of light by the sodium. It also turns out that fireworks, they also display these light emissions and very similar to what we see in the flame test. In fact, many salts are used to prepare fireworks. As I said before, there are 4 emission lines in the visible region for hydrogen. J.J. Balmer showed that the wavelengths in the visible spectrum of hydrogen could be reproduced by this very simple formula here. So 1 over the wavelength is equal to R, which is the Rydberg constant, and that's 1.097 times 10 to the negative 2 reciprocal nanometers. Another way that you'll see this in other textbooks is 1.097 times 10 to the 7th reciprocal meters, okay? But in your book, they're using nanometers. In most other books, I see this used. So I'm going to follow your book. Now, n is a positive integer, and it has to be greater than 2. And what we can do is, from this formula, we can determine the 4 wavelengths in the hydrogen spectrum that corresponds to the visible region. Let's go to the next slide here, and we can talk about that. Here we go. Here's our equation again, and you will be asked to use this. And for each of the 4 lines in the spectrum, we can substitute n equal to 3, 4, 5, and 6. So let's go ahead and do that for n equal to 4. So 1 over the wavelength is R times 1 over 2 squared minus 1 over 4 squared. And this gives us 0.00205687 reciprocal nanometers. So this corresponds to this. I want the wavelength. So what I have to do is divide this by 1, and this corresponds to 486 nanometers. 486 nanometers is the blue-green line in the hydrogen emission spectrum, which you can see in that figure on the previous slide and also in your book. So go ahead and try this for n equal to 3, 5, and 6. You'll be able to obtain those other wavelengths. Sound good? So go ahead and try that. You'll probably be asked to do that somewhere. Another way that we can represent the formula is the same as before. We have 1 over the wavelength as R, and rather than a 2 here, we have this M. And this is the level of lower energy orbit, and so this would be, of course, the level of higher energy orbit. I'll show you what that means in just a moment. All right, so we talked a little bit about Rutherford's nuclear model, and it's based on the fact that the nucleus has most of the mass of the atom with a positive charge, and around that nucleus move enough electrons to make the atom electrically neutral. There was actually a problem with the model. Using the theories at that time, it could be shown that an electrically charged particle, or an electron if you will, that revolves around a center could continuously lose energy as electromagnetic radiation. As the electron loses energy, it would eventually spiral into the nucleus. That would mean that the atom is not stable. So this model does not explain the stability of the atom. It also did not explain a line spectrum, because according to this model, because the atom is continuously losing energy, we would have a continuous spectrum. Niels Bohr suggested a model that could predict the existence of line spectra. What he did, he used both Planck's and Einstein's idea about quantized energy. These postulates accounted for the fact that an atom is stable and does not continuously radiate energy and spiral into the nucleus. We observed the line spectrum of hydrogen. So here are the postulates. The energy level postulate, let me move this down a little bit. An electron can only have specific energy values in an atom, and these are called energy levels. Each energy level is a fixed circular orbit of the electron about the nucleus. The higher the energy level, the further the orbit is from the nucleus. And let me move this over a little bit. And you can kind of see this here. So you can think of the nucleus. And then here we have n equal to 1, n equal to 2, 3, 4, 5, 6. And the electrons are supposedly orbiting in these stationary orbits. Let's go back here. The second postulate, the electron's energy will remain constant as long as it stays in a stationary state. So that makes sense because we know now that the electron does not spiral into the nucleus. So that means that as long as the electron remains in a particular energy level or a stationary state, that its energy is going to remain constant. And then there's number 3. The electron can change to another stationary state by either absorbing energy or emitting energy. So by absorbing a photon or by emitting a photon. So the energy of the photon is the difference between those two states. So the final energy plus h nu is going to equal the initial energy. So what we can say is that the energy of, let's say, an emitted photon is, we'll call that delta E, and that's going to be equal to h nu, which is initial minus final energy. So that's the energy of an emitted photon. When a photon is emitted, that means that the electron is at a higher energy level and it drops to a lower energy level. That's when we see that light if it's in the visible region. Okay, we'll see those colors like with the strontium and the flame test. Now, if a photon is absorbed, then your final energy is going to be greater than that of the initial energy because the electron is going to go from a lower energy level to a higher energy state. Anyway, with his formula, Bohr was able to predict all of the lines in the spectrum of the hydrogen atom, not only in the visible region, but also those in the infrared and the ultraviolet regions. Now I want you to remember that quantization of energy in an atom is the result of an electron not being able to reside between those orbits, okay, according to that Bohr model. So what we want to do is go to this slide here. I'm going to take a look at this diagram. I can barely get the whole thing in here, but that's just going to have to do. Let me bring this down a little bit. All right. Let's take a look at this. This is for the hydrogen atom. And for the hydrogen atom, electrons that move, let's say here we have n equal to 1, 2, 3, 4, 5, 6, all the way to infinity. Okay? And so let's say electrons that move from n equals 6, n equals 5, n equals 4, n equals 3, all the way to n equal to 2. Okay? So those are these lines here. These result in the emission spectrum of the visible region. So those 4 lines that we saw for hydrogen. We call this the Bohr series. Electrons moving from n equal to 6, 5, 4, 3 to n equal to 1. So right here, okay, that'd be these lines right here. These would correspond to the photons that are emitted in the ultraviolet region of the electromagnetic spectrum. And for hydrogen, there's 1, 2, 3, 4, 5 of those. Okay? And we know that the ultraviolet region of the spectrum is higher in energy than the visible region. Okay, and then here we have electrons moving from n equals 6, 5, 4. Here there should be another line corresponding to n equal to 6, n equal to, there are more lines here. That should be underneath this, n equal to infinity. So electrons moving from n equals 6, n equal 5, n equal 4, down to this n equal to 3 level. Well, these correspond to the infrared region. So these would be the lines that we would observe in the infrared region of the spectrum, which of course is less energetic than either the visible or the ultraviolet region of the electromagnetic spectrum. Bohr was able to determine all of emission lines for hydrogen in the UV, in the visible, and in the infrared regions using that formula. So use the formula, and now I'll show you the way to use that formula. So we have 1 over, the wavelength is r, and it's going to be 1 over m squared minus 1 over n squared. Okay, so for emission in the ultraviolet region, m would correspond to 1 for the UV region. Obviously for the visible region, m corresponds to 2. So that's for the visible, corresponds to 2. And then for the infrared, m would correspond to n equal to 3. So it would correspond to 3 in the infrared region. And then remember that n in this formula must be greater than m. Okay? So go ahead and practice using this information to determine the lines in both the ultraviolet and the infrared portion of the spectrum for hydrogen. Something else I want you to notice here. Notice the difference between, here we're going to look over here. These are energies. These happen to be in kilojoules per mole. And notice the difference in energy between n equals 1 and n equal to infinity. Okay? And it's 1,312 kilojoules per mole. So in other words, it takes 1,312 kilojoules of energy to remove electrons from 1 mole of hydrogen atoms. So what does this mean? Well, notice that these numbers have negative signs in front of them. There's no such thing as negative energies. This is done by convention. This 0 point here, where n is equal to infinity, at this point here, the electron is separated from the hydrogen atom. This corresponds to the ionization energy. So the difference between the n equals infinity and n equals 1, this 1,312 joules, that is the ionization energy. Also notice that these energies decrease as we get to higher energy levels. Okay? And that's the case. Think about it. That electron, the higher the energy level, the further away it is from the nucleus, the further away from the influence of that nucleus, if you will. All right, n equals infinity, the electron is separated from the hydrogen, and this is the ionization energy. Another way to look at this, it depends how you're looking. Are you looking at a transition from n equals 1 to n equals infinity? Or so that would be the ionization energy. But if you're looking at it from n equals infinity down to n equals 1, then that means that when an electron is added to a hydrogen ion, there's 1,312 kilojoules of energy released. Turns out energy is released when electrons are added and absorbed when electrons are removed. That makes sense because you need energy in order to remove an electron. According to Bohr theory, the emission of light from an atom occurs when an electron undergoes a transition from a higher energy level state to a lower energy level state. Absorption of energy occurs when an electron undergoes a transition from a lower energy state to a higher energy state. Emission of energy occurs when an electron goes from a higher energy level state to a lower energy level state. That's when we observe emission. So going back to absorption, how does an electron get to a higher energy state? In a hydrogen atom, the electron will reside in the lowest energy state, which is n equals 1. Actually, the lowest energy state is called ground state. Okay? That's the ground state. In order to go to a higher energy level, we know the electron must absorb energy. We call this excitation. We say the electron is excited to a higher energy level. How does this happen? Well, number one, it can happen when two hydrogen atoms collide. So basically, some kinetic energy of one atom can be gained by the electron of the other atom. So thereby, that excites the electron from n equals 1 to a higher energy level. Which energy level is going to depend on the amount of energy. Excitation of atoms and the emission of light is most likely to occur in a hot gas. The atoms in a hot gas are going to have very high kinetic energies. Now, let's say an electron in a hydrogen atom undergoes a transition from n equals 3 down to n equal to 2. Then that would mean that a photon of red light is emitted. And it's emitted at a wavelength of 656 nanometers. When red light of a wavelength of 656 nanometers is shined on a hydrogen atom, where the electron is in the n equals 2 level, then a photon can be absorbed. That energy gained by the electron will undergo a transition from the n equal to 2 to the n equal 3 level. So that would be the reverse of the emission process. It turns out that all materials that have color appear colored because of the absorption of light. So when white light falls on a substance that absorbs red light, the color components that are not absorbed, meaning the yellow and blue light, are going to be reflected. And guess what? The substance looks blue-green. All of the postulates that we have discussed also apply to other atoms besides hydrogen. The only difference is we cannot obtain the energy levels by a simple formula like we can for the hydrogen atom. But if we know the wavelength of emitted light, we can relate that to the frequency of the light and then to the difference in the energy levels of the atom. Energy levels of atoms have been experimentally determined in this way. Some limitations of the Bohr model. Number one, you can't predict the spectrum of any other atom than hydrogen. It's only going to work for one electron species. Species like hydrogen ion, helium ion, lithium 2+ ion. If more than one electron exists, we have to take into account the other interactions. For example, electron-electron repulsions. This leads us, all these observations and solutions lead us to quantum mechanics and quantum numbers. We already know one quantum number, and that is n. Our current ideas about atomic structure are dependent on the principles of quantum mechanics. This theory applies to very small particles of matter, like electrons. Before we talk about quantum mechanics, we need to discuss the de Broglie relation. So the de Broglie relation, what is it? Recall that Einstein stated that light has both wave properties and particle properties, and that we can characterize that light by its wavelength and its frequency. Remember, we know that a photon has energy equal to h times the frequency. But think about it. De Broglie also stated that the photon must have momentum. Momentum mc. And we can actually relate this to the wavelength like so. De Broglie postulated that a particle of matter with mass and speed, and we'll use this letter for the speed, has an associated wavelength just like light. So the wavelength is equal to Planck's constant divided by the mass times the speed of the matter. This is called the de Broglie relation. So what does this mean? It means that matter has wave properties. But why don't we ever observe the wave properties of matter? Well, let's see why. If we use the de Broglie relation, if we have a ball that is 0.145 kilograms moving at 60 miles an hour, it has a wavelength of about 10 to the minus 34 meters. Let me show you how to do this problem. We'll use this equation here. So the wavelength is going to be equal to Planck's constant times 10 to the negative 34 joules times seconds. And we'll divide that by the mass, which should be in kilograms. So 0.145 kilograms times the speed, and that should be in meters per second. So that would be 27 meters per second. And let me put this into my calculator. Remember, the units of joule are kilograms meters squared per second squared. So that's why we need to convert the mass to kilograms. And I get a wavelength of 1.69 times 10 to the negative 34 meters. Well, it turns out we cannot detect small wavelengths like this. So obviously this does not mean much, when we talk in terms of matter displaying wave-like properties, because we can't even observe a wavelength this small. But for electrons, it's a different story. We have an electron moving at some speed, and their wavelengths are about 10 to the negative 12 meters. So those we can observe. Well, on Monday, I'll continue with Chapter 5. We'll start at Section 5.6. Then we'll talk about the Heisenberg uncertainty principle. Everyone have a good day.